Welcome to our demo. We're going to explain you how our data analysis tool works for extracting insights from defaced web pages. In our particular case, what we had was a bunch of CSV files, and in particular we had metadata describing 13 million defaced web pages. And we wanted to understand exactly how the attackers were creating these pages and what kind of content they were putting on, etc., etc. So our first choice was on the back end. We opted for Elasticsearch due to its scalability and popularity in our community. And our main contribution in this work is that we created a distributed pipeline that can be attached on top of Elasticsearch in a way that it's customizable for the user, that is flexible, and it doesn't hinder scalability. So you still have the same scalability that you have with pure Elasticsearch. What we have is a lightweight wrapper on top of it so that a programmer can easily create distributed processing tasks. As a nice addition to the tool set, we created a visualization web app that an investigator can use, as I said before, to dig into the data and understand what kind of tools the criminals are using, which techniques they were preferring, or what campaigns, and etc., etc. What we want to find out is, for example, who are the hacking groups behind these web pages, what kind of techniques they use, which target they hit, and basically if there is a way to intelligently cluster similar defaced pages or different defaced pages that have been attacked in the same way. What we had at the beginning was something like this. So this is a CSV file, which this is, for example, one line explaining when a certain defacement record was recorded, which is the name of the attacker, the declared name of the attacker, which was the target website, the IP at the time of the defacement, and some other metadata describing the context of the intrusion, for example. And then we also had a snapshot of the original page right after the defacement. As you can see, we have nearly 13 million records, and this is the first and simplest view that you can use. You can basically browse through the data. You can think of this as an augmented version of Kibana. So basically, you can browse through the data, and you can issue queries directly using Elasticsearch Lucene query. So, for example, if you want to find out all of the pages that do not have black among their colors, you can issue a query such as this one, and basically exclude all the pages that do not have screenshot colors among black. Given a set of attributes, we pull up interesting features such as the number of style attributes, the number of anchors, the number of URLs, the number of hashtags, the number of scripts, the number of sound URLs, the number of Twitter handles, the number of images, etc., etc. And the goal of this is essentially to represent each page as a vector of numbers. So if we were using a classic clustering technique to directly apply it on this feature, most of the time we will end up having a scalability issue, in the sense that having 13 million records and having to compute the distance metrics between all of these features, we're going to end up spending a lot of time simply to materialize this distance metric. So instead of approaching the problem in a classical way, we approach the problem in a slightly approximate way, but still, given the results that we obtained, we were pretty happy about the performance. So given each of these features, instead of using them directly, we look at their distribution. So we look at, for example, the number of styles throughout all the documents. We look at how this value is distributed. So you can see that most of the document, actually 60% of the document, has 0 styles, and then 27% of the document have one style element, and so on and so forth. And we do this for all of the features where this makes sense. So all the numerical features. We have integer features and also floating point features. So given this distribution, now intuitively you can tell that we can divide all of this domain into buckets, into bins. So we will have a bin that we call low, we have a bin that we call medium, and then we have a bin that we call high, and then we have a bin that we call outlier, which is way above the where the vast majority of the documents lie. So given this principle, we apply this reduction basically on all of the features, and what we end up having, if we go back to the previous, is a series of buckets. So for each feature, we have a bucket that is represented as a letter in which that feature lies. So for instance, the number of styles in this case is very high with respect to the rest of the data set because it is 9. And most of the documents we have seen that do not have nine style element. And the same applies to other numerical features. If we represent this in a visual way, you basically have a colored vector that tells you immediately where your page is positioned with respect to the rest of the dataset. And at this point, the clustering task becomes an aggregation. I want to group all the elements given these dimensions, and you can select flexibly the set of dimensions that you want to use. And what's happening behind is actually simply a classic aggregation query, nothing different than that. So the approach is completely transparent and applicable to any Elasticsearch installation. For instance, if you want, you can change the attributes that you use to cluster, and you can even cluster for all of them at the same time. Then the time spent for clustering doesn't change a lot. And the idea of this is that the more records you want to cluster, if you're noticing that the performances are not satisfactory, you can simply add more hardware to the problem, and the algorithm will scale automatically. So you don't have a cap such as the maximum amount of memory that can be installed on a single machine, because you can distribute the workload entirely. So you can have like an installation of 100 nodes of Elasticsearch and distribute the aggregation problem.
In the second part of the episode, we're going to show you how we can use our system to run very efficient and precise cybercriminal investigation or analysis on web attacks. So as Federico was mentioning, one of the features of our system is to extract contextual information on the page, like for example the Twitter handler included in a page, as well as telephone numbers or email address. So any piece of information that can be used to track down or do attribution on a specific attacker. So let's start by looking, for example, at those pages that contain a Twitter handler referring to Operation France. So Operation France is an ongoing hacking campaign targeting mainly French language-speaking countries since over the last 5 years. And we've seen actors going from Turkey to North African countries or Islamic countries, mainly targeting, or actually mainly doing attacks for religion reasons. So they're mainly religious motivated. So by looking for this, we can look for all the pages including these hashtags, and you can see there are more than 1,000 of this. And for example, let's open one of this. Of 2014. So this is a defacement of a specific French site, as you can see here, and it's been hacked by Red Spy. So this is one of the actors of this team. As you can see here, there are all the names of the team involved in this campaign, and they pretend to be Turkish, and they pretend to be affiliated with, as I was saying, Operation France. So the question here could be, for example, how we can, study more in depth this campaign to try to understand from when the campaign start, when the campaign finish, which are the type of website being defaced and by whom. So to do that, we move to the clustering panel of our web application, and we perform the same query we have seen before here. We run it, we wait for a couple of seconds, and the system returns us a list of clusters that are basically a representation at high level of the different campaigns related to Operation France. As you can see, these are mostly concentrated in 2015 and 2016, with some going back to 2013. So we can open one of these. And here we can see a list of defacement records of this cluster. What we can also see, interestingly enough, is a list of attackers that contribute to the campaign. It means that these are the actors that somehow are affiliated to the same group. So we can go from a single actor, as we were seeing before, to more than one actor. We can also see the list of domains being targeted, and of TLDs, with France being one of the main ones. Another interesting query we can run on our system is in particular related to the attack that have been done end of 2015 against the Bataclan music club in Paris, that is somehow related to this Operation France. So we can do here, we can do a query by keyword, and by specifying also the timestamp. So from 01, from 1st of 2015 to the end of 2016. Alright, so what the system tells us is that there is a cluster of 36 web pages being defaced by a single actor over a target of 31 different domains. So we can do a breakdown of this. We can see that the attacks that are being run pretty much the same day, which is like the 5th of January of 2016 up to the 2nd of January. We can open the page, and we can see that, as I was saying, here that's an attack that has been done in memory of attack to the Bataclan with the logo of France. There is also some music. And this is also shown here by this one that indicates that there is a sound URL included in the page. So this is just a simple example. Of course, the system will allow you to query anything you'd like. And the fact that we use Elasticsearch for doing this type of, for running this system makes the search very efficient and rapid. Thanks for listening, and have a nice day.